Okay, so let's look at acid-base theories. Last year I think you had 2 acid-base theories. I think this year there are 3 acid-base theories. So let's have a look at the first acid-base theory. So Mr. Arrhenius came up with a theory. An Arrhenius acid is a substance that releases protons in an aqueous solution. So HCl goes to a proton plus chlorine when you add water. An Arrhenius base is a substance that releases hydroxide ions in an aqueous solution. So you can see here sodium hydroxide goes to a sodium ion and a hydroxide ion. So this is just the acid-base theory. You have to learn this. This is the definition. They can ask you any of them. You just have to know them, okay? So remember when we talk about, here is the example of what's the difference between ionization versus dissociation, okay? So in ionization, you actually have to form an ion, and dissociation, you are already an ion and you are being split up. So HCl is actually hydrogen chloride gas, but if we add it to water, it splits up into a hydronium ion and a chloride ion, and this was covalent. These two are ionic, okay? So it's a covalent to ionic thing, so this is ionization. Can you see here is an example of this? Here's the water, and this water's got the lone pair over here. Here is the HCl, and then the chlorine is very electronegative, so it's already almost got all of the hydrogen's whole one electron is almost totally stuck on this chlorine here. And then when the water comes along, because opposite charges attract, this little proton here, the hydrogen, gets stuck onto the water, and here you get your hydronium ion and your chlorine ion, okay? So this is ionization of hydrogen chloride to form protons and chlorine ions in solution. But if you wanted to have sodium hydroxide or something, it dissociates because it's already ionic, and then the moment you put water in there, the water just separates it out. Nothing here is actually losing or gaining electrons. They already did it before the water came along. But here, the water is causing ionization. Here's the sodium hydroxide. When we dissolve it, all that happens is, look at all the little polar water molecules. Here's my positive sodium ion, and the little polar water molecules come up to it, and the slightly negative end of the water molecule just separates out all of the sodium ions from the hydroxide ions. So you can imagine all of the little water molecules piling up around the sodium ion and pulling it off, and then others of them will pile up around the hydroxide ion and pull it off, and then they just go into solution, and this is called dissociation, okay, because they were all associated and now they are not associated, they are dissociated. Then we come to a new theory, acid-base theory. So Arrhenius's definition is only for aqueous solution. So old Bronsted-Lowry, these are 2 people I think, came along and they said no, an acid is something that donates a proton, and a base is something that accepts a proton. So if you have a look here, ammonia, NH3, is a Bronsted-Lowry base, and water can be a Bronsted-Lowry acid. And here is this ammonia, okay, and it has accepted a proton from the water, so it is a Bronsted-Lowry. It's become accepted a proton to form the ammonium ion, and the water is the Bronsted-Lowry acid because it donated the proton to the ammonia. Okay, so it's just a different theory, because this one can be if you're not in aqueous solution. Obviously the example's got water, so it's aqueous, but there are other situations where this becomes important. Remember as well, we're going to talk about acid-base pairs. Okay, we have an acid, a conjugate acid, and a conjugate base. So this is the general theory. Here's a proton. Anything that's got a proton is an acid, so all acid formulas start with H. Here's H bonded to some anion, and then along comes the base, and the acid gets onto the base here, and then the little anion's left by itself, and here we've got our conjugate acid on the other side. So let's talk about the different kinds of acids you can get. So look here, monoprotic and polyprotic. Mono is one, poly is many. This protic comes from the word proton. So this is one proton. This is lots of protons. Okay. So we can either say an acid is monoprotic or polyprotic, depending on how many protons it can donate. Okay. And if you are a polyprotic acid, you lose your protons one by one in steps. So hydrochloric acid, nitric acid, and ethanoic acid, they've all, look here, only got one hydrogen that can be taken off. And so they just lose their one hydrogen as a proton, and that's how they form an acid. But sulfuric acid, carbonic acid, and phosphoric acid, look, the little white balls are the hydrogen. So here's your SO4 sulfate ion, and here are the two hydrogens bonded to it. One of these comes off, and then the other one comes off, and so that's why it is a diprotic acid. Here is a carbon bonded to 3 oxygens. Okay, so this is a carbonate ion with 2 hydrogens on it. So this hydrogen can come off and become a proton, and this hydrogen can come off and become a proton. So this also can donate 2 acids, this carbonic acid, which we find in soda water, and acid rain. And here's the phosphoric acid from Coca-Cola. So this little orangey thing here is the phosphor, and these 3 are the oxygens, and here's 1, 2, 3 hydrogens, and so first one hydrogen comes off, then the other one, then the other one. So it donates protons in a stepwise fashion. Here, have a look here. We're going to go like this with the phosphoric acid. Here's a bigger picture of the phosphoric acid. So the first thing that can happen is we lose one hydrogen. Look here, H3PO4, H2PO4 minus. So when you take away one positive charge, because the proton has a 1 positive charge, you are left with 1 negative charge. So this little hydrogen over here has popped off and become donated to something else, because remember, acid is a proton donor. And here we have this H2PO4 minus, and then what happens is another one comes off, and now we've only got the phosphor and the 4 oxygens and 1 hydrogen, and so we've lost 2 of the initial hydrogens, look, initially, and they're gone here. So this is HPO4 2 minus, because the loss of 2 protons makes it 2 minus. And then finally the last hydrogen goes in the last step, and you're just left with the phosphate ion, poor little lonely phosphate ion, and this phosphoric acid has donated 1, 2, 3 protons. That's why it's a polyprotic acid. You must also bear in mind that all acid-base reactions, you can't just get an acid reaction and a base reaction. It is always an acid-base reaction. They occur simultaneously. There's always one thing giving up a proton and the other one taking the proton. Okay? So an acid-base reaction involves the transfer of a proton from an acid to a base, and can also be called a protolytic reaction. So here's the base, here's water acting as an acid, here's this proton that's about to get transferred. Look here, the lone pair here takes this proton from the water, and we end up with an ammonium ion and a hydroxide ion. So when the acid donates its proton, we get what's called a conjugate base. Now this general equation here, you need to remember this general equation here, because they'd love to ask you what's the conjugate base of this acid. So the acid, it loses its proton, okay, or donates its proton and leaves behind the conjugate base. And its acid, the acid has a conjugate base, and a base has a conjugate acid. So look here, here's the water. This water is the acid. It's donated a proton and it's left behind with OH, which is OH minus, which is its conjugate base. And this ammonia here, it's going to accept a proton, which makes it a base, and here is its conjugate acid. And this is called a conjugate acid because this can again lose the proton. Okay, so you could look at an NH4 plus ion, ammonium ion, as an acid. So it's a conjugate acid of the ammonia base. You need to spend some time with this so you get this clear in your own head. What is an acid? What is a base? What is the conjugate base? But basically, if you get an acid and you take the proton off it, you're left with the conjugate base. So the acid minus H gives you conjugate base. So the base is the opposite to the acid. The base accepts the proton, and then what you're left with is the conjugate acid. So here, you can't see this J on conjugate because the picture zoomed up. Don't worry about it. Here's the acid. Here's the ammonia, which is the base. So the base receives a proton to form a conjugate acid. So this base grabbed the water's proton and formed the ammonium ion. So ammonia is the base, the ammonium ion is its conjugate acid. So, goodness me, there's still a long way to go. Let's stop here and then do this separately.